Hello guys, so myself Prabhanshu Sharma, and today I will discuss my interview experience of Nuclear Power Corporation of India interview for executive trainee position through GATE 2026 examination. And so my location for the interview was Anushakti Nagar, Mumbai, in the Mayur guest house, and it is close to Chembur region of Mumbai. And coming to the criteria which Npcil used for shortlisting the candidates, it was GATE 2026 scores for respective disciplines, namely electrical, ECE, mechanical, civil, chemical, and I think few more branches were there. So interview was for 100 marks, and it was purely based upon interview marks. Like the person who scores more marks in interview will get selected irrespective of the gate score, because gate score is just used for shortlisting, not it has no weightage in the final merit. So my time was around 6:20 p.m. in the evening to 7:04 p.m. Around 44 minutes of interview was there, and date was 17th of June. My branch is electrical engineering. Now coming to uh, basic things. So firstly, when I entered the room, they asked me what were my favorite subjects. So I told them network, power system, control system, and power electronics. But to my surprise, they didn't ask any question from control systems. Rather, they asked from electrical machines. So you should be ready for such surprises. Also, they asked some questions from digital electronics. So all in all, they asked from about 5 subjects. So you need to prepare at least 5 subjects thoroughly. Let's move to the question number 1. So I was given a chalk and asked to go to the board and solve a basic network transient question, and in which there was a supply and there is a bulb connected in parallel to an inductor. This bulb is B1, and then this bulb is B2 connected in parallel to this capacitors, and there is a small resistance and a bulb B3 connected in series. All in all, this was the arrangement. So question number 1 was at t equals to 0 plus. At t equals to 0 plus, like for 1 second, there is a mistake here. I need to add a switch here. So a switch was just closed at t equals to 0, and at t equals to 0 plus, we need to tell which bulb will be on and which one will be off. So coming to the solution, so as we know that as we just close the switch, the inductor comes open circuited and this capacitor becomes short circuited. Also, let me draw the circuit completely. Okay. So as we can see, this bulb B1 will be on and B2 gets shorted, so it will be off. Also, there is a path for current to flow, so B3 will also be on. So B3 is on, B1 is on, and B2 is off. Now at t tending towards infinity, this inductor becomes shorted, and let me read out the circuit. This capacitor becomes open circuited, and this B1 will become on, B1 will be off, B2 on, and B3 is also on. So this was a solution. Now coming to question number 2, a lady member was there which to my surprise asked a question from digital electronics. So it was a question about drawing a staircase switch and explain its working. So I knew about a staircase switch. If you guys don't know, let me tell you, it is it is a different name of XOR gate. XOR gate we study in digital electronics, that only is there. For example, its representation is AB bar plus A bar B, or we can also write it as like this. Now we need to draw this circuit. So at that time I could only draw the truth table and explain them that we can use XOR gate. I was not able to explain the proper single pole double throw switch, or like how can we realize that. I just tried to draw one switch which I will represent here. So if this was A and this was B, so since we have AB bar and these two are in multiplication, so we need to when we know this AB bar is there and it is an addition to A bar B, so this two should be in series, like this A circuit and this thing B bar should be there, and it should be in parallel to this A bar. A bar B. Okay, so if we have a normal supply here connected to a small load here which we want to give power to, here we are using supply. These are the control switches. So basically what I did, I can feed this and I can feed once again I can just simply one second, I will use a different color here. Let's say yellow. I can just connect the opposite of this to this. Also I can connect this to this, and also I can simply I can just remove this, and for example we want to go from here to here, so connected this to A, and can simply take a complement and connect it to this. So this is the whole arrangement I made there, but the panel member was not satisfied, and I checked it. We need to draw some alternative switch, which I didn't remember at that time. So I think I was not able to fully solve, but I was able to explain the basic mechanism. So moving on to the further questions. So the next question given to me was draw the VI characteristics of NSCR. So let's draw it. So as we know, simply just draw it roughly. This current in microamperes, this current in milliamperes, this voltage in volts. Also we know that for different gate currents you can get different breakover voltages, and after that we know that it just goes like this. So this is latching current, and this is somewhere holding current. and we can further draw it and represent the breakdown voltage. This is V break over voltage 1, V break over voltage 2, V break over voltage 3, and this is for some current Ig1, this is for some current Ig2, this is for some current Ig3. So as we know, if we increase gate current, charges increase. And in electronics, you might have also come across this relation that breakover voltage is inversely proportional to the doping. So if we increase the doping, breakover voltage decreases. So since Ig1 is lesser than Ig2, lesser than Ig3, so similarly we can see that breakover voltage 1 is more than breakover voltage 2, is more than breakover voltage 3. There is an inverse relation here. Now further they asked me, what in SCR and GTO, whose latching current will be more? So this was a very interesting question that they asked to me. So for that we need to simply just get the basics of the structure. Like this question can only be answered with the help of the internal structure of GTO and SCRs. Then only it can be answered. So for that, since I knew the answer, I have read somewhere. The basic fact is GTO is having more latching current. I was not able to explain exactly why it is having more, so I was only able to comment upon these things. Now coming to the 3-phase full wave rectifier. In this, they asked me the working of the 3-phase full wave rectifier. So firstly, I just draw a 3-phase full wave rectifier circuit. So, 1 minute. So I just give the supply here. This is phase A. This is phase B. And then there was a phase C also, or you can say R by B. So this was the structure, just naming them. This T1, T3, T5, T4, T6, T2, and then they were connected to a load. And this was the polarity. Okay, this is my output voltage, and this was my supply, 3-phase supply, 50 Hertz, 3-phase 50 Hertz AC. Okay, so now let's move on to discuss the working of it. So working. So for this, there's a short trick. If you can remember, it will be very helpful. There's a concept of concept like this. So basically, from 0 to, if we just consider alpha is equals to 0 degree here, they asked me to just consider alpha is equals to 0, so it was basically acting like a diode. So even if it is not, I can explain, but keeping the case very simple, the firing angle was 0 degrees. So just remember, go VCB, then VAB, and now B has repeated 2 times, so just remove it, so it becomes VAC. Now A has also repeated 2 times, so just remove it, it becomes VBC. Now C has repeated 2 times, so just remove it, this becomes VBA. And similarly, now we can see B has repeated 2 times, so just remove it, we can see we get VCA. And now A has repeated 2 times, when we remove it, it becomes VCP. So we just move on to this. So this is how the mechanism works. So then he asked me if V output is equals to VAC, if V output equals to VAC, which of the thyristors will conduct. So to that, if you look at the circuit, if V output equals VAC, that means from the top group, that is T1, T3 and T6, this one second, I will just remove it, we will use a different color here. If you see that this from T1, T3 and T6, in this group 1, and this is T4, T6, T2, this is group 2. So in the upper half there will be only one device conducting always, and in the lower half there also will be only one device conducting always. And this is because if 2 devices conduct same time, there will be a problem of short circuiting of the supply, and it will be leading to the damages of the thyristor. So it is a basic explanation. And now coming to the question that if the output voltage equals to VAC, that means which thyristors will be conducting. So if the output voltage is VAC, this T1 from this upper group and this T2 from the lower group will be conducting. That was the answer. Now they asked me a question about this pulse control circuit indirectly, but I moved them to this 3-phase rectifier working and this switching scheme, and also few more questions, and but I was not able to answer this pulse control circuit. I was not able to draw, I didn't know about it. So if in case you just get stuck on something, just try to tell them whatever you know about that concept. Like I didn't know about the pulse control circuit, but I explained them this working very well, so they might have given me some marks there. If otherwise I have left that, I wouldn't have got those marks. So I think it is very important to know your strengths, and do not try to bluff. Try to tell them whatever you know about that subject, about that topic that they are asking. So let's move to the further questions. So question number 5 was HVDC versus HVAC. So what are the basic differences by when will we use HVDC and when we use HVAC? So if you know, HVDC is used for synchronizing grids or interconnection of power from different countries. Suppose someone manufactures some power in USA, and someone manufactures some power in let's say Australia, and these two countries want to trade some power between them, electricity between them. So by using HVDC we can easily synchronize those power, we can easily move on the power because of two reasons. It has having frequency of 0, that it is DC, so its frequency is 0. It is easy to connect those two grids and transfer the power. Also, at higher distances HVAC is costly and has more losses. This is the main reason why we don't use it for higher distances, and that distance at which we start using HVDC, because it becomes less costlier than HVAC, is known as break-even distance. So I explained them this. Then they asked me about the corona and skin effect. So if you know that skin depth is directly proportional to 1 upon under root mu sigma and omega. Okay, so in this, sigma is conductivity, omega is frequency. So if skin depth, that means suppose we have a conductor here, and through it if you look at it, through it some current is flowing. Okay, so for DC supply, for DC, this frequency is 0, so the skin depth is tending towards infinity. That means the current is concentrated from this center to this edges. So it is not concentrated to only one region, it is concentrated overall. But in case of AC, what will happen? This current will get concentrated only on the edges. And why so? Because frequency will be, let's say it is 50 Hertz, so skin depth will be some finite number, and it will be concentrated only around the edges. Due to this, resistance increases and we have more power loss. Also, corona effect is more because it is also proportional to frequency only. So in that they also asked, like for DC, if we want to reduce corona, what will you do? This was their cross question. If you want to reduce corona in DC, what will you do? So as we know that electrons are liberated, or we can say, if let's say I'm just redrawing this, just removing it. Okay. That the electrons are liberated when there is corona discharge. So if we use negative polarity, in DC supply, these electrons will repel and corona effect reduces. So this is the full explanation about how can we can use the negatively for negative polarity DC supply, which will repel the electrons and it will lead to lesser corona discharge if we want to further reduce the corona in DC supply or in the HVDC supply. Then the next question was about basic surge absorber and lightning arrestor. What is the difference between them? So basically lightning arrestor is used to basically if you want to remember it in short, you can remember like it is having a partial behavior for power frequency. For frequency it shows very low resistance. It is having very high resistance. That means it does not allow that power to flow through it. But for you can say high frequency or surges, it has very low resistance path. So basically it makes an alternative path for current to flow. So this is a whole explanation about it. Now let's move on to the other questions. This was the basic question. The second was, what is surge absorber? Surge absorber is also similar kind of, but it is used to reduce the steepness or slope of dV by dt curve. Like sometimes it happens that in a very short time the voltage increases very high, so due to that the lightning arrestor may not work, and to reduce this, there is a surge absorber placed before the lightning arrestor to counter this effect and make the dV by dt curve more steep, less steeper, that is reduce its rate of rise, and through this we can ensure that our lightning arrestor safely works. And let's move on to the next question. So there was a very basic network circuit also given. In this we had to analyze few components. So here you can see there is a supply and also there is a resistance. This resistance is very small, in like its value is very small magnitude wise, and there is an inductor placed, there is a bulb, and there is a capacitor. So now let's look at the question. The question was, draw the waveform for this inductor current and capacitor current. This was the question. We have to draw the waveform. It's a basic question. So let's analyze the circuit. You can see that let's redraw the circuit, and at t tending towards just after, let's say for one more error is there. Here I have to place a switch. They also place a switch here. So there is a switch which is closed at t equals to 0. Okay, now I have to analyze what will be my behavior of this capacitor current and this inductor current. What will be its waveform? It's as simple as that. So for that we can assume that this bulb is purely resistive in nature and ignore its inductance, they said that to consider only the resistance of the bulb. And now let's analyze. So we have a switch, we have a supply here which is like this, and at t equals to 0 plus, what will happen? This inductor will get open and it will be like this, and this resistance RB, it will be there, and this capacitor will get off. So we can see that at capacitor current at t equals to 0 is equals to t equal to 0 plus is equals to Vs upon RB. Okay, 1 minute. Yes, so we know that the capacitor current at t equals to 0 plus is Vs by RB. Now at t equals to infinity, t tending towards infinity, the circuit will be like this. This will be Vs, and then there will be a resistance R. This thing will get shorted, like inductor will get shorted, and there will be a resistance of the bulb, and the capacitor will get open. So current through capacitor automatically becomes 0. So if we know that for writing the basic equation of current and voltages, we can use the following thing. So IC infinity here is Vs by RB. It is not Vs by RB, it's 0. It's 0 plus Vs upon RB into e की power minus t by tau. Now here tau is the time constant, which is equals to, this tau is equals to what? Let's analyze what is the value of tau. So for this we just need to short the, here I can show what is the value of tau. Just short the supply, the resistance will be there, the inductor will also be there, but you can just ignore it. And so if you look at it, here we have a shorted supply. Now we have to look through this capacitor and find the equivalent resistance. Okay, so if you look at it, this, because of the shorting of this resistance, the only thing it will see is this resistance RB. So the time constant is RB into C. So you can write the equation of capacitor current as Vs upon RB e की power minus t upon RB into C. This is the basic equation of the capacitor current, and if we want to represent it in graph, we can easily do it. It will be a decaying exponential having maximum value as Vs by RB. This is my capacitor current and this is my time t, as it is in seconds. This is in amperes. This is amperes. Now let's look at the inductor current IL. So for that, if you look closely at t equals to 0, circuit, we can see that it is open. That means IL 0 plus is equal to 0 ampere. But if we look at the t equals to infinity circuit, t tending towards infinity circuit, we'll look at this. We get this capacitor is open. That means all the current will flow through it. So just writing the KVL equation in this loop, if we get Vs minus Just neglect this R because it is mentioned in the question that this R is very low, so we can technically neglect it and approximate it to 0, and through this Vs minus VL, that means voltage across this VL equals to 0. VL will become equals to Vs. Now VL is what? L dIL by dt is equals to Vs. So L dIL is equals to Vs dt. Now basic thing is this: L dIL will come Vs upon L dt, integrated at t equals to 0 till a certain time t, and at t equals to 0 this current was, as we know that this inductor current IL0 plus, as we wrote, was 0 ampere, so we can safely put it 0 ampere, and at certain value it will be IL. So IL will be equals to Vs by L into time t. So it will be linearly charging, like linear equation circuit will be there, so linear graph will be there. So if we draw the graph, it will become this IL in amperes versus time t, and it will be a straight line like this. And if we draw IC as well, it was like this. This is my IC, this is my IL. So at certain point they will be equal. So they asked further questions on this, but I was not able to explain upon this point. I was able to explain till this much. Now let's move on to the question number 8. This was a question on synchronous motor. What are its uses? So basic uses: it is used as a synchronous condenser. That means at no load and overexcited condition. Let me explain you basic thing. We can write the reactive power equation of motor, that is synchronous motor, as 3 Vt by xs Vt cos delta minus Ef. This is my basic equation of motor. So if we increase the excitation, that is if we increase Ef, we know this term will become negative, and overall Q motor will become negative. Now as you all know, motor is there. Motor is to absorb reactive power. It is there to absorb reactive power, but here it's coming negative. That means it's supplying reactive power. That's why it is used as a power factor correction. It is also used in power factor correction. We can it can be used to compensate the inductive nature of the our system. Now what are its drawbacks? So its main drawbacks: it is not self-starting. That is the main drawback. And how can we remove those? By use of this variable frequency drive, and by also using this damper windings. Okay, so now they asked me to draw the V and inverted V curves. So what is basically the V curve? It is a curve between the V curve. It is a curve between this armature current and field current at constant active power. And what is inverted V curve? It is curve between, what is it? Curve between power factor and this curve between power factor and this IF or excitation change at same P equals to constant. Now let me draw this curve, basic curve you need to know. Just drawing the V curve first, and I am drawing it for synchronous motor. This is my IA, this is IF, and this all is in ampere. This is also in amperes. Now it's something like this, okay, and as we try to increase the load, it will try to go upwards and upwards and upwards. Like if we are increasing the load is all increasing here, the curve will get upper. This is at unity power factor, this dotted line. If we increase the excitation, like if we go above, like go this way, this arrow way, the excitation will get increased. And as we saw previously, if we increase the excitation here, the motor's reactive power becomes negative, and reactive power is negative, then the power factor will be leading. So we will get leading power factor in this region, and we get a lagging power factor in this under excited region of synchronous motor. So this was the V curve, and now drawing the inverted V curve. It is also similar, just inverted V curve, but here the main component we need to understand here, it is power factor. This is power factor cos phi, and if we try to increase the load, it will gradually shift. This curve will move towards right as we increase the load at constant power. So this is basic thing. This dotted line again represents the unity power factor. Now let's move on to our final question, which was a 3-phase induction motor torque slip curve, and they further asked me about its VFD control and its resulting characteristics. So let's first draw the basic torque slip characteristics. So if you look at it, this is my torque in Newton meter, and this is slip, and following this slip, this is at starting conditions. So we know that slip is equals to ns minus nr upon ns. At starting, rotational speed will be 0, so slip will be 1, and here slip will be 0. Here the rotation speed is 0, and here the rotation speed is equals to ns. As we know that if these two are equal, no EMF will be cut, no current will be induced, and that's why EMF will be 0, and for resulting torque will also be to 0. This is my motoring mode. This is my generating mode, and this is my braking mode. Now if we further look, they asked me about the VFD control of this synchronous this induction motor, 3-phase induction motor. Now there are two types of control. Firstly, we can keep the ratio of V by F constant, and we are decreasing the value of V and F. For example, if voltage is 230 volts and frequency is 50 hertz, okay, so now we take the voltage as 115 volts and frequency as 25 hertz. But the ratio here is same in both the two cases. The ratio will remain same, but we are decreasing the value of voltage and frequency both. In this, they asked me to draw the new new torque slip characteristics. So firstly, since we know that synchronous speed ns is equals to 120 f by p, so since we are decreasing the frequency, our synchronous speed will decrease. So what will be the effect of this on the curve? So in this curve, our synchronous speed is coming somewhere here, but it will shift towards left. It will come somewhere here, or maybe even left side. Now let's look at some other parameters in this characteristics. It is one of the most important, that is the maximum torque, and this is the starting torque. Okay, so if you have studied induction machine even from any teacher, you just remember this formula, that the this starting torque is directly proportional to v square upon f cube, and this maximum torque is directly proportional to v square upon f square. Okay, so since the ratio of v by f we have seen is constant, so we can write it as v square upon f square into 1 upon f. So this is k square into 1 by f. So we can see that the starting torque is equals to k square upon f, where k is a constant. Now we are decreasing the frequency, that means the starting torque increases. Okay, also this is directly proportional to, this maximum torque is directly proportional to v square upon f, is directly proportional to v square upon f square. So we can write it as k square, so it remains same. Now redrawing our original circuit, how will it become? It will be something like this. Firstly, I'm drawing the previous circuit. I'm only drawing this motoring mode only. Here, earlier, in the earlier case, this mark is for earlier that I draw in the previous page. It was like this. Okay. Now I will use this purple ink for our new, that is VFD1 curve. This is our torque. This is slip and speed respectively, like this. This is slip equals to 1, this is slip equals to 0. This is rotating speed equal to 0, rotating speed equals to synchronous speed. Now in the new curve, one more aspect we need to study, that is the slip at maximum torque, and we know that it's directly proportional to, that is, it depends upon the ratio of r upon x. So now x is what? It is mainly inductive, so we can directly write it as x directly proportional to frequency. So slip at maximum torque is also directly proportional to r upon f. Now if we are decreasing frequency, our slip at maximum torque will increase. That means if for this, that is, this was slip at maximum torque for case 1, so it will move more on the left side. Torque will remain same, but it will move on the left side. So now just redrawing the final final curve. Our starting torque will increase. One second. Our starting torque will increase our maximum torque will remain same, and our slip at maximum torque 2 will also improve, that is 0 to 1. This way it is increasing, like this way slip is increasing, so it will move leftwards. And since our synchronous speed also decreases, it will go somewhere here. So this is the final curve. That's all about my interview. Thank you guys.